I'm going to do the sequence of partial sums, and basically what it says is if you have a sequence, an infinite sequence starting at either 0 or 1, it doesn't matter, but going to infinity of a sub n, then it will either converge to or diverge depending on what the partial sum does. So you can say that the sequence of partial sums, this sequence will be equal to the limit as n approaches infinity of s sub n. And so for the series a sub n, the first partial sum is just a sub 1. The second partial sum is a sub 1 plus a sub 2. Third partial sum a sub 1 plus a sub 2 plus a sub 3, so on, so on. The nth partial sum is a sub 1 plus a sub 2 all the way up to a sub n. And so we can find this formula for basically any series, and if we evaluate the limit of s sub n, say that the limit of s sub n converges to a finite number, then we know that the series will converge to that finite number. If the limit of s sub n diverges, we know the series will diverge. So there's two different sides to this test. The first is the test for convergence. With a basic formula that we have here, 1/2 to the n, we know that's a geometric series, and we know that it converges because the inside is less than 1. But it's a simple form that we can apply to the sequence of partial sums. So if we start this at 0, go to infinity, the first partial sum is 1, because 1/2 to the 0 power, anything to the 0 power is 1. The second partial sum is 1 plus 1/2. 1/2 to the 1 is 1/2, so it's 1 plus 1/2. The third partial sum, which is s sub 2, because we started at 0, 1, 2, 3, 4. The third partial sum is 1 plus 1/2 plus 1/4. When you plug in 3, I'm sorry, not 3, but when you plug in 2 for n, you get 1/4. So it's 1 plus 1/2 plus 1/4, and so on and so forth. And you can continue to do that, and then you start to recognize a pattern. We can see that the pattern here is factor of 2, factor of 2, factor of 2, factor of 2 for the denominator. And for the numerator, it's a factor of 2 minus 1. And it's also twice the size of the bottom plus minus 1. So if this were 32 over 16, it'd be a half. If this were 16 over 8, it'd be a half. 8 over 4 would be a half. 4 over 2 would be a half. So we have 2n plus 1, and that gets us double of 2n. So 2 to the n plus 1 is double of 2 to the n, and then minus 1 on the top to make it 31 instead of 32 over 16. And this is our s sub n. If we evaluate the limit as n approaches infinity of s sub n, we can break this in half, so we can put the denominator under both top sides of the numerator. So we have the limit as n approaches infinity of 2n plus 1 over 2 to the n minus 1 over 2 to the n. And we know that 1 over 2 to the n will go to 0. We know that this will go to 2. So we know that this series will converge to 2 because the partial sum approaches 2 on this limit. Another thing we can do is test for divergence, and here's kind of a basic form we have here. The infinite sum, or the infinite series starting at 1 of natural log of n plus 1 over n plus 2. Now we already know natural log rule of two things divided, we can subtract them. So it's natural log of the top minus natural log of the bottom. Now we're going to find our partial sums. If we plug in 1 for our n values, we get natural log of 1 plus 1 is 2 minus natural log of 1 plus 2 is 3. That's the first partial sum. We do this again, we have the first sum plus, when we plug in 2 for n, so it's ln 2 minus ln 3, that's what we had up here, plus plugging in 2, we get ln 3 minus ln 4. And you can see you have minus ln 3 plus ln 3. Now we do it again, we get the same thing, plugging in 3, we get ln 4 minus ln 5. ln 3 cancels, ln 4 cancels, we're left with ln 2 minus ln 5. If we did this forever and ever, we would have the first one, and all the last ones would cancel except for the very, very last one, which would be ln 2 minus ln n plus 2. This is kind of like a telescoping series, but it still applies here for partial sums, because we can see that the partial sum of this series is represented by ln2 minus ln n plus 2. So we take the limit as n approaches infinity of ln2 minus ln n plus 2. We know that if we put in infinity for n here, this would be natural log of infinity, which will go to infinity. So we basically have ln2 minus infinity, which goes to negative infinity. This series will diverge because the limit approaches negative infinity, which is divergent. And those are the two ways you can use the sequence of partial sums.